Are you trying to adjust equations where some elements reduce or oxidize in an aqueous solution? Well, this is what we are going to learn in this video. Before commencing, I consider that you are familiar with adjusting standard chemical equations, as redox equations are more challenging. If this is your first attempt to balance equations, you should learn how to balance standard equations first. I have on my channel another video showing that. Let's start. A redox equation is a chemical equation where there is a transfer of electrons between two elements. For example, we can produce sodium chloride when chlorine reacts with sodium in the right conditions. This is an example of redox equation. In this case, the sodium loses electrons and the chlorine gains electrons. The reaction where an element loses electrons, like the sodium, is called an oxidation reaction. The reaction where an element gains electrons, like the chlorine, is called a reduction reaction. To remember oxidation and reduction, we can use the mnemotechnic word, oil rig, which stands for oxidation is losing, reduction is gaining. Some redox equations can get complicated, mainly when it is in an aqueous medium and the water is part of the reactants or the products. To adjust redox equations, we are going to divide these depending if they are in neutral, acidic or alkaline solutions. The most common method is using half equations. These are the oxidation and reduction reactions. Reactions in neutral conditions are the easiest to adjust, sometimes can be done with visual inspection and do not require the use of the half equations. The steps to follow are, first, identify the elements that are reduced and oxidized. Write their half reactions. These are the reduction and oxidation reactions, balancing the elements in the reaction and the relevant number of electrons. Second, adjust both half equations to ensure that the number of electrons is the same. Third, add both half equations. Fourth, the same number of electrons should appear as reactants than as products, canceling each other. Let's see how this is done with an example. We will balance the reaction of cuprous ion with iron to obtain ferric ion and copper in neutral conditions. The half equations are, reduction, cuprous plus 1 electron to obtain copper. Oxidation, iron to obtain ferric iron and 3 electrons. To equalize electrons, we multiply by 3 the reduction reaction. This will give 3 electrons in both half equations. When the electrons are equalized, we add both equations together. And we cancel electrons and other chemical species that appear in the equation. In this case, their only common terms are the 3 electrons on each side of the equation. Finally, to ensure that the equation is balanced, we check that the same number of atoms appear in the products and reactants. We have 3 atoms of copper and 1 atom of iron on each side. And the number of charges is 3 on each side. Therefore, the equation is balanced. Now, we move to balance equations in acidic conditions. These tend to be more complex than neutral solutions. The steps using half equations are, first, identify the elements that are reduced and oxidized. Second, write their half reaction, balancing the elements except for the hydrogen and the oxygen. These will be balanced in the following steps. Third, balance the oxygen atoms by adding the appropriate number of water molecules to the opposite side of the equation. Fourth, balance the hydrogen atoms by adding protons to the opposite side of the equation. Fifth, add the charges on each side and electrons to equalize the charges on both sides of each half equation. Sixth, compare the number of electrons in each half equation. If the number is different, multiply by a convenient number to make them equal. Seventh, add both half equations. 8. Cancel the electrons, which should be the same number on both sides, and any common terms in reactants and in products. As example, we are going to adjust, in acidic solution, the reaction of permanganate with iodide to produce manganese 2 and iodine. In the first step, we identify both half reactions. As the manganese in the permanganate has an oxidation status +7, and as ion appear as +2, it is therefore the element that reduces. On the other hand, the iodide, with an oxidation state -1, changes to iodine with an oxidation state 0, is the element that oxidizes. In the second step, we balance the number of atoms, except for the hydrogen and the oxygen. In the reduction we have one atom of manganese on both sides, therefore we don't adjust anything there. In the oxidation, we have 2 atoms of iodine in the products, therefore we need 2 atoms in the reactants. In the next step, we balance the oxygen by adding water. In the reduction, we have 4 atoms of oxygen in the reactants and none in the products. To have in both sides the same atoms of oxygen, we add 4 molecules of water to the products. There are no changes in the oxidation. With the oxygen balanced, we now proceed to balance the hydrogens. We do this by adding protons. In the reduction, we have 8 hydrogens from 4 molecules of water and none in the reactants. We balance them by adding 8 protons to the reactants. We don't need to balance the oxidation. With all the elements balanced, including oxygen and hydrogen, we now balance the charges by adding electrons. We start with the reduction. In the reactants we have 1 negative charge from the manganate and 8 positive charges from the protons, giving a total of 7 positive charges. In the products, we have 2 positive charges from the manganate ion. To balance reactants and products, we add 5 electrons in the reactants. In the oxidation, we have 2 negative charges in the reactants and none in the product. We balance the charges by adding 2 electrons in the products. At this point, we have each half equation balanced in terms of atoms and electrons. The next step is to equalize the number of electrons in both of them. In the reduction, we have 5 electrons. In the oxidation, 2 electrons. If we multiply by 2 the reduction and by 5 the oxidation, we obtain 10 electrons on both half equations. With both half equations balanced, and with an equal number of electrons, we add both equations. You can pause the video for a moment to see it. The final step is to cancel electrons and common terms. We have 10 electrons in the product and reactants, we cancel them. There are no other common terms to cancel. We have balanced the equation. However, it is advisable to check that it is balanced by checking that each chemical species and charges are balanced. We start with the manganese. As we can see, there are 2 atoms of manganese in reactants and another 2 in the products. We balance now the atoms of oxygen. On the reactants, we have 4 atoms for each molecule of permanganate. As we have 4 permanganate molecules, we have a total of 8 oxygens. On the products, we have 8 molecules of water, each contributing with 1 oxygen, therefore 8 oxygens. Next, we balance the atoms of hydrogen. In the reactants, we have 16. In the products, we have 8 molecules of water with 2 hydrogens each, therefore, we have also 16 hydrogens. The final atom to check is the iodine. In the reactants, we have 10 iodide ions. In the products, we have 5 molecules of iodine, each with 2 atoms of iodine, then, the products also have 10 atoms of iodine. We now check the charges. In the reactants, we have 2 negative charges from 2 permanganates, 16 positive charges from 16 protons, and 10 negative charges from 10 iodates. Adding all together gives a total number of 4 positive charges in the reactants. In the products, we have also 4 positive charges provided by the 2 manganese ions. Therefore the equation is balanced. Balancing reactions in alkaline solutions can be done following similar steps to the acidic conditions. but adding hydroxide ions and water. However, I find easier to follow the same steps than in the acidic conditions, using the result obtained by adding the following steps. First, add, on both sides of the equation, as many hydroxides as protons are in the final equation. Second, each hydroxide and each proton on the same side of the equation cancel each other to form one molecule of water. Third, cancel any other common terms in reactants and in products. We are going to balance, in an alkaline solution, the equation of the reaction between permanganate and iodide to produce manganese 2 and iodine. It is the same reaction that we used in acidic conditions, and we will start from the result obtained there. As in the original result, we have 16 protons in the reactants. We add 16 hydroxides on each side of the equation. In the next step, we form water by adding the hydroxide and protons together. In the final step, we eliminate common terms. In the reaction, only water appears on both sides of the equation. We have 16 molecules of water in the reactants, and we have 8 in the products. We can eliminate 8 molecules on each side, and the equation is balanced. When the equation is balanced, remember to check that the atoms and charges are balanced. You can check that in each side of the equation we have 2 atoms of manganese, 16 atoms of oxygen, 16 atoms of hydrogen, 10 atoms of iodine and 12 negative charges. I hope that this video has helped you with an introduction to balancing redox equations. The best way to learn them is by practicing, so I leave below a link to my webpage, where you can find more examples to practice. It is free and you don't need to register. As I'm planning to carry on uploading more videos and expanding my website, if you have any questions or would like to see any other chemistry-related topic, please leave a comment here or on my webpage, as it will help me to help other people. If you liked this video, please click like, as it will help to continue uploading videos. Thank you very much for your attention, and I wish that you have a very good day.